Hi, I'm Mladen Sormaz. I'm Head of Football Analytics at Leicester City. The title of my talk today is Practical Tools for Bridging the Gap. Just a little summary of who I am. Originally started off in sports science and football coaching. Went and did a PhD in neuroscience and started in analytics in about 2016 when there was a lot of public data available. Went to a few hackathons and then left to work for 23 Sports in 2018, working part-time Huddersfield Town as a data analyst, and since 2019 I've been head of football analytics at Leicester City. So the whole point of the talk today, this sort of backs onto a conference we hosted in 2020, and it was called Tactical Insights, Bridging the Gap. And what we had there was a nice mix of coaches, tactical analysts, data analysts, data scientists. And the whole point of that conference was to try just show what the workflow looks like when you merge everyone together and they work together. And I think we had Barcelona and a couple of other sort of big names there showing us how it's done. And so today is just building on that, hopefully with a couple of practical examples of how it can be done. First half of the talk's going to be more process-based, and then second half of the talk's just got a couple of potential methods people might be interested in. So the first thing that got me thinking about the bridging the gap thing was this article by Tom Worville in 2019. And it hit up on a really good point, which is in that football, there aren't really a lot of people in the position of data translator who are there to merge between practitioners and sort of hardcore data science. There's a bit of debate on Twitter after this about whether it needs to be a role. But having read that, I think the minimum we can all agree is it definitely needs to be a skill and a really key part of the process. So after having read this, we had the conference, and then I was sort of thinking about how the conference went. And I saw this talk by Joe Mulberry at the Seattle Sounders Analytics Conference. And it was really interesting because up until then, I'd only thought of bridging the gap from the point of view of data to practitioner. But he made some great points about, as a scout and as a football practitioner, how many things in terms of player judgment and intuition are actually quite similar to when you model data. So his sort of crib notes on what intuition was when it goes well and how you spot a player was you update it over time with new information. You can add new variables to your understanding of football, and generally you sort of weigh and filter new information based on context. And so after seeing this, I thought actually the translation doesn't only go data to practitioner, it sort of goes back again and informs models. And after having read those two things and hosted a conference, I read that, which was a book that is basically about an organization, Houston Astros, who'd already tried doing this. They developed a system called Stout. It was half stats, half scout. And the most interesting thing about this was it wasn't presented the way that analytics versus the eye test usually is. It was a system of integration rather than having them separate and having them fight it out. So that became really interesting. And so the talk today is hopefully going to cover a few things inspired by those three talks. So at the moment, sports analytics does have a bit of a sort of image problem, especially as it sort of popped into the mainstream without a lot of mainstream explanation. So with data modeling, it can sometimes just seem like a magic number that's come out of nowhere, and it starts slipping into commentary, starts slipping into athletic articles. Before you know it, you can't enjoy football anymore. But while that's only partly true, the reason is because advanced analytics can seem like a bit of a black box. As far as a lot of people are concerned, you just start with some raw data, somebody does some maths, and then there's a model, and you're just supposed to say, that model's correct. And the big problem there is that even when these things are presented, validated on the data side, there's not always the conversation and the translation through to football practitioners to sort of understand why it's even being done. So sort of taking a step out and zooming out of the sort of three ideal areas that are part of good data analytics or data science, there's what from this famous diagram is called hacking skills, basically having a computer genius on your team, maths and statistical knowledge, and substantive expertise. And in the middle of that Venn diagram, you can see that's the ideal for what data science should be or analytics should be. And this area is the most key, and it's not always presented too much at football analytics conferences. So I'm going to hopefully take you through a few slides here of where this expertise and translation comes in the ideal process at a football club and how that ideally works. So thinking of the data analytics process, I've got a 4-step model here. I'm going to show you where translation comes in and where it's really important. So the first step of any sort of data work is data engineering, infrastructure, architecture. Investment in that is vital. It's the baseline that you build all of your analytics on and all your scalability on, and ability for people to access information quickly. Arguably, that needs the least amount of football knowledge and translation. It does need some, but there are other skills that are much more important there. The next step, though, is sort of data modeling and enrichment. So this is the first step where you're starting to get importance in people who do have some knowledge of football and understanding, especially in the data enrichment. So that's usually just coming up with a better description of your data from your raw data based on what you know about football. And then these last two steps, they are where translation is absolutely vital. So there's usually a point at which you've built your architecture, you've built your models, you've explained your data nicely, but you need some sort of way to expose that to people who are going to use it. And that's usually through some sort of dashboard or web app. So you're at the point where you need skills of basic UI design and an ability to translate advanced stats into an actual workflow for all different types of practitioners. Then the final step, sometimes this is merged with the third step, but that final step is delivery of the actual stats. And the key thing is it's always got to be integrated with other mediums. Especially in football, things generally always go back to video if you found them in data. So presenting them alongside is key, and having expertise in that is why a lot of the time this can be done by performance analysts, technical analysts on the scouting side. But of this whole workflow, the two areas where translation is absolutely vital, and arguably the most important, is these final two. Because you can do the first two steps at a world-class level, but without this final bit working, it's not going to be leveraged, it's not going to be put into strategy. So this is where most of the translation needs to happen. It's absolutely critical. So I'm going to zoom in on those two areas. So although I've shown it as just a one-direction flowchart, this is actually a continuous process of sort of exchange of ideas and feedback between sometimes two sets of people, sometimes a team of people. And they've all got different responsibilities within this. So the first one for the sort of data scientist, modeler, analyst is you've got to track relevant domain knowledge. That's fancy language for make sure you keep learning about football the longer you work in football, and make sure you incorporate that knowledge where it's appropriate into models. After that, the next most important thing as part of your translation duties is simplifying explanations of complex models whilst keeping them accurate. And finally, and a step that's sometimes forgotten, is you actually need to track the use of analytics and aim to innovate. You can't just create dashboards into the void and hope they're being used. You actually need to follow that up, see if there are points of failure, and see what's really being sort of used well. So that's on one side of the equation. On the other side of the equation, it might be the same person, but usually it's a different person who'll do the sort of delivery to a practitioner. And they've got a different set of translation sort of priorities. The first one that's often forgotten too is tracking feedback from the practitioners. So if there's a gap in knowledge, a gap in explanation, anything like that, that sort of needs to be fed back into the data science analysis team so that things can be simplified or presented in a different way. Another one is ensuring concepts from the data model are well explained. It's kind of analogous to the one on the other side of simplifying explanations, but generally on this side you have the people who are more on the people person side of things. So knowing how to deliver it to different practitioners based on how they are, their level of buy-in, stuff like that is key. And the final one, again, another important one, it's usually this person is somewhat of a filter of the information to the practitioners. So it's really important for them to balance and communicate the integration of data into the workflow and make sure that they're presenting the relevant data at the right time to the right practitioners. Don't present everything all the time, otherwise you just become another source of noise, effectively. So that's sort of a quick sort of tour through why I wanted to do the talk on this topic, where the idea came from, and sort of how it works in the process. I'm going to basically tell you why you would even do this. So the most basic unit data analytics can affect a sport is actually on the field. So there's a nice visualization here. As NBA has adopted sort of analytics over the years, the top 200 sort of shot locations have changed. It's like a classic image, but that's over 20 seasons, and that's not possible without what I would say the hardest level of translation, which goes from the hardcore data modeling to the actual practitioners who set strategy in-game. More recently, there's another example. This comes from Next Gen Stats, and this is fourth down decisions now that are happening in American football. And again, you can see there's been a sort of trend change over the last 5 years. And again, that's one that comes from effectively modeling probabilities to explaining in-game live when a decision should be made. So all the talk of maybe bridging the gap every time I mention it, this is the ultimate, like, smallest unit of actually changing the ecosystem and the way the game's played. It's not the only way to affect things with analytics, but it is probably the one where you're having an actual impact on the way the game is played, so it's the smallest unit. So these next 2 bits of the talk, I'm going to present sort of 2 different ideas and frameworks of communicating different things that are important in analytics. So the first one is going to be a section on a method you could use to bridge the gap of communicating a predictive model to a practitioner. So this comes from the idea of, like I said, expected goals to some people just popped out of nowhere. So I'm going to talk through a model like that and how you could explain it if you're showing it to someone for the first time. And the second one is about bridging the gap between models. So this comes from that idea, sort of inspired a bit by the Houston Astros. I'm sure it's not the same method, but it's just an idea of how you can actually merge and compare different data models and the human model. So beginning with the first method I'm going to talk about, it's explaining expected goals. The only reason I'm doing this is it's probably the most widely known advanced stat in the room. But this actually is 2 different shots with the exact same expected goals value. Sometimes they're presented in static images like this. And really, to look at it, if you didn't follow data modeling and you didn't know what underlies it, it could just be confusing. Even if you know that distance is supposed to be a good thing, distance to goal, you probably don't know about all the other contextual things that are different at each shot. So this first method I'm talking about is coming from the point of view that in football, shots are basically the most important thing in the game, but they're also very low frequency. So sometimes when you're analyzing things, when you've got your data mined on, you're actually analyzing something from a very small sample and feeding that back to a practitioner. So here's a way that we can sort of do that. And it comes from Shapley Additive explanations of models. So there's a paper relatively recently by Lundberg and Lee. And what they did was they tried to take something out of game theory and put it into sort of explaining predictive models. And so the way they did this is, got an analogy here. Basically, it's useful in any situation where you've got a team effort that's supposed to produce one value. So in this example, you've got a coalition, a team effort, which is a team of people pushing a car, and they're trying to produce a value, and that value is the movement of the actual push car. How far does it move? So this method is an attempted way to try quantify the individual contribution of every member whilst they're all pushing at the same time. So the analogy here to a model is, you have an expected goal value that is an output from a model, and you have the correlation, which is everything you put into a model. And there's actually ways of explaining things on a much smaller sample that I'm going to talk through. So just to sort of give a very sort of basic overview of how this thing works. So imagine you've got the pushing the car example. You've got 4 people, and you've got a distance moved. So the 4 people here are like predictors in the model. The distance moved is the outcome. That's the prediction. What we do is we just take people out, and we look at a change in the value. So you can see there the gray line is how far the car would have moved. The black line is how far it did when you take that person out. You do get that again with the second person, put the first one back in, and you can see all these values change because everyone has a different contribution. And then you don't just do that, you then just do all the possible sort of pairs of combinations, take them out differently. And at the end, what you hopefully get is a value that basically explains how much each person on average has contributed. And you find that out by taking them out of the model. So that's a non-football example. The reason it applies to our expected goals model is earlier said that, you had that map with 2 different shots that had the same value. There was no explanation there of why that value was like that. So you might have someone who's quite informed about expected goals and knows the different rules of thumb of how you produce a good expected goals value. So they might know that shooting close to goal is good, shooting centrally from good angles is good, and also shooting without too many bodies behind the shooter and the goal. And that's fine, but as we move to more advanced modeling, when you've got a more different situational context, just looking at the distance on a static map might not be great. You might actually need to explain each example, especially for the outliers, if a practitioner asks you, why is this one different to what I expected? So let's give an example. We've got a 5-feature expected goals model with like 5 classic things. You've got distance from goal, angle to goal, impact height, whether it was a 1 versus 1, or whether they were shooting into an open goal. All things we'd expect to change the sort of probability of a shot being a goal. So what we do is we'd basically substitute out our coalition and our values. And so for our coalition, you've got those 5 predictor features. And for the values, you've got the actual expected goals prediction. So the next step is basically just finding out, for each one of these shots, what if we want to know which was the most important thing for determining that expected goals value? Well, the reason we want to do that is because we want it to be interpretable. So what the value will show us is how much each predictor contributes, whether it's a positive or negative effect on the outcome variable, why each case and each shot receives its prediction, and basically you're trying to increase transparency. So to talk through a practical example here, you've got an outcome of a model with its Shapley values. So the ones in red, as they increase, they have a negative effect on the expected goal value. The ones in green, as those values increase, they have a positive effect on the value. So straight away you can explain, you can do this with most models, but you can explain that as distance goes up and impact height from the ground goes up, it's harder to score a goal, which we already know. But you can actually see the relative contribution. As an angle increases, if it's a 1-on-1 and if you've got an open goal, again, 3 obvious things, but as those are present or larger, you have a positive correlation with the expected goals value. So let's have a look at 3 different shots and what this actually means in practice. So imagine that we've had a game where we've had something like 10 shots. Someone's looked at an expected goals map and they're not quite sure why we've got the values we've got. They can come and ask you, and you can break it down. So for example, we had one shot here that had an expected goals value of 0.36. You can see the size of each one of those pink bars tells you the importance of each part of the situation at the time and how much is contributing. So you can see that we had a close shot to goal, it was a 1-on-1, and it was a good angle. So that's why that was a good chance. And you can explain that to a practitioner, and they fully understand why the model's saying what it is. It's not just some black box. Another example here, it's another shot, much higher expected goals value. The contributions here are like how far away from goal you are. You're much closer. It's actually an open goal, so it's an easy chance, and it's a great angle. And here you can actually see in the blue what's actually sort of taking away from the expected goal value. It's that the ball's slightly off the ground, so it's a slightly harder finish. And then finally, you can do that with really bad sort of quality efforts on goal. So here you've got one that's 0.04, and in the blue bar you can see that's what's having a negative effect and what's dragging it down as a chance compared to the baseline. And you've got that it's a far away shot from an average angle. Now, the point of showing this wasn't to just show you how expected goals works, but this is more of a framework about how to think when working with practitioners. Whatever the model is, especially if it's predictive, case by case, for example, you might have something that predicts whether you're going to win a game, your win probability. Case by case, at some point, you're going to be asked to go back in time and look at things individually or in smaller samples. To be able to explain why a prediction comes out is much better than just saying what the actual value was. So to give a practical example here too, here's something we can do. So, this is the one with the gap. There you go. So let's say you want to do a sort of model output SHAP value driven cluster analysis. What you could actually do is take all the contributions to each chance individually and feed those into a clustering algorithm. So instead of just picking up some basic things like the location of the shot, you can actually pick out different types of situation where different underlying variables were contributing really well to the probability. So for example, cluster 1 here picked out a couple of situations where it was a 1 versus 1, and that's the thing that contributed most to it being a really good chance. And the blue dots there are just shots where the fact distance to goal was small and angle was good, so that's what contributed. So what you can see here now is you can even start to split your subset of data based on questions from a practitioner sometimes. So you might get a question like, why does this striker get his good chances? And before you've even looked at the video, you can section this up. So that's just one example, but like I say, the main point is just thinking about this framework when you've got any predictive model. Being able to explain every single case is a massive benefit, especially when you're trying to get buy-in. So moving on to the next talk section, thinking about bridging the gap between models. So this is a slightly more complicated analysis that I'm going to talk through. But this is based on the sort of idea of how do we compare models in a way that's user-friendly to a practitioner, and how do we compare what the human eye sees versus a database model. So it comes from a thing called representational similarity analysis, which comes from neuroscience. And this was from about 2008. And what they were trying to do was compare different types of models from different brain scans. So from different people, different species, sometimes by computer-generated algorithms. And this provided a framework to actually compare these in the same space. So let's use a practical example, go straight into a football example. Imagine you've got ratings for each of the big 5 leagues, one on the average game tempo, one on the average game physicality, and one on, say, the average opponent difficulty. It's a very common sight just to see a list of numbers when you're looking at analytics, and sometimes the best thing you can do there is just a bit of conditional formatting or just ranking them. But what's really hard to see there is all the different relationships between all those different pairs of numbers and how the leagues differ all in one snapshot. So a way around this is to do a similarity analysis. And what you can do here is kind of like what the human brain does. You have a baseline league and you compare it to another league. So here you'd say for tempo, what's the average difference between a Premier League game and a Bundesliga game? What's the average difference between a Premier League game and a La Liga game? And you just do that for every single pair of leagues you've got in your sample. And then you do that for the physicality, and then you can also do that for the difficulty. So at that point, you've got a bunch of sort of similarities between leagues, and you can actually visualize them in one shot. So let's say you've got the 3 different models there. Each one of these squares represents a correlation, or sorry, distance between 2 leagues in terms of similarity. So let's take that top left black square as an example. The reference league is comparing the Premier League to Bundesliga. And here the model could be saying that it's a very dark color, which means they're not very similar in terms of game tempo. So that's what that square means. But on a different model, you look at the same comparison again. I think this one's the physicality difference. There's a brighter color in the square. And that represents that actually these are slightly more similar. And the final one, you've got the league average opponent difficulty difference. And it's saying that actually, again, they're less similar. There's a bigger difference in your average game difficulty between the Premier League and the Bundesliga. So the whole point here is you go from that list of numbers to actually being able to just present these even in isolation. And a person who just has it simply explained what you're actually trying to measure can immediately start seeing what are the similarities and differences between different leagues. So as well as giving you some sort of comparison of leagues, it can be quite interpretable. So that's not the end, that's not the final step. So that, again, can be quite a lot of information. There's a way to simplify that and just present it in a one-shot. So let's say we take one of our models. I think this is the physicality model. You've got your distance matrix, which we've seen on the last slide. So what we can actually do is instead of having this axis where you've got 5 leagues down one side and 5 leagues along the bottom, you can just flatten it using a technique called multidimensional scaling. You can flatten it into just one space, like a 2D map, almost like a scatter plot. What you can produce for yourself is something like that, which is a 2D map. Imagine that's a scatter plot. And what it does is, at the same time, it considers the difference between every league simultaneously, whilst flattening it into a map that you can interpret. So there you can see how similar Premier League is to La Liga, whilst at the same time seeing how dissimilar it is to Liga. So we've gone from a list of numbers that were ratings to a visualization that can help you pick out similarities and differences, to a one-shot thing that condenses down a whole bunch of different similarities and differences just into a 2D scatter map. So that's not the final step. There's other things we can do with that. So imagine you've got these 3 models, and you don't know whether you need all 3 of them or whether they're all telling you the same thing. You can actually put them into their own comparison space. So the next step is saying you've got your league difficulty model, your tempo model, and your physicality model. As you might expect, your tempo and your physicality models are much closer in terms of their similarities and what they're telling you. So this gives you a sort of way to actually compare models in the same space without having to look at every single similarity square, without having to look at every single pair of numbers. You can just flatten it down into this, and the distance basically tells you how similar these things are. So that's comparing models. And I said earlier on that there's an aspect where you can compare models and humans. Well, it's not too different, those the similarity models, to the mental models people have of football. Let's say we have 6 people here, and they've all rated 8 players in the same pool. You can turn their ratings into similarity distances. So brighter squares there, that's 2 players that viewer thinks are quite similar. Darker squares are players that the viewer thinks are not very similar at all. What you've got in each one of those squares is their mental model of the whole scouting pool of players that they've looked at. So when we think back to what we just did with the other models, we can condense down 6 people's opinions across 8 different players into something similar to what we saw with the models. So you can actually start visualizing opinions, how similar these people's opinions are on players, where they live in comparison to the models. And you can imagine applications yourself. I'm not going to suggest them, but basically you have a way of condensing a whole load of different information just into that 2D chart. And the point of this isn't at all to say that people should be thinking like models or anything like that, but I think it's useful to know when you've got a process, what you're measuring differently through different means, what you're measuring similarly through similar means. So this is basically to just open up some thinking. I'm not saying this method should be used by anyone or is the best, but this is more just a framework about how it could be useful to think about data and what scouts provide over the next X amount of years, because everybody already knows that data has blind spots, and people already know like what weaknesses in the eye test can be. It's boring to just keep saying those 2 things for the next 15 years. What we can actually do is try get a handle on it, merge the processes together rather than having them be adversarial in an argument. So that's my talk. I whizzed through it. Thanks for your attention.